So this is my presentation. Basically, it was about predicting protein misfolding and disease associations using machine learning. So the goal of this project was to use machine learning.
Your presentation, your screen share just.
Oh, I'm sorry. I've been having some errors with my computer with that. So thank you for letting me know. I'll just share again. Sorry.
No, it is. You can relax.
All right. So the goal of this project was to use machine learning to identify misfolded proteins or structural abnormalities in proteins that could be linked to genetic or neurodegenerative diseases by analyzing their 3D structures. So this project matters so much because proteins need to fold into precise 3D shapes to function, and when these proteins misfold, they can cause or signal diseases like Alzheimer's, Parkinson's, Huntington's, and more genetic disorders. So detecting these structural errors early could lead to earlier diagnosis and treatment. So basically, I wanted to kind of describe the process of this project. So we used a machine learning model to analyze protein structure data, specifically the root mean square deviation between the protein's actual shape and its ideal or expected shape. RMSD equates to how off the structure is. So if the RMSD is low, then the protein has a normal healthy structure. However, if the RMSD is high, then there's a high chance of protein misfolding or mutation. So when it comes to data collection, we found a dataset on Kaggle, which contained detailed measurements of protein tertiary structures, which are the three-dimensional shapes that proteins fold into. This dataset includes RMSD, which is root mean square deviation, which is a quantitative measurement of how much the protein's actual structure deviates from its ideal folded state. This helps identify misfolded proteins. The dataset also includes features F1 to F9, which are numerical descriptors that represent various physical and chemical properties of the protein structure, such as folding energy, hydrophobicity, solvent accessibility, sequence length, and more. So this was my exploratory data. In the first couple sentences, it's going to be a little repetitive if I explain them, but it's basically what I explained in the previous slide. So I explained that there are no missing values in the data set and that all the features are numerical, which made the data great for statistical modeling and machine learning. So after my preliminary inspection, I realized that the dataset is clean and free from obvious duplication. However, some features, especially those reflecting energy or structural complexity, may contain outliers due to the natural variability in protein structures, but overall the dataset was complete, high quality, and ready for further analysis, with RMSD serving as a good target for evaluating protein folding accuracy. So when it comes to data cleaning, I tried to include a video of my code. I'm not sure if it'll play because I was having some errors with it earlier. However, later on after the presentation, I could go through the code and show it to you if you'd like. But when it comes to data cleaning, I included a written summary on the left side. So basically in this code, I removed duplicate protein entries. I handled missing coordinates, standardized protein names and labels, normalized RMSD values, and filtered extreme outliers. And then when it comes to feature engineering, our instructor wanted us to focus on feature selection and handling missing values. So instead of raw sequence data, which is unavailable, the model uses the dataset's numerical features F1 through F9, which represent physical and chemical properties related to protein folding, stability, and structure. And when it came to handling missing values, any missing values in the dataset, in the features, they were filled with the column mean to maintain dataset completeness and avoid errors during model training. So when it comes to the AI model itself, I coded the first one on Collab and then I made an actual application in Streamlit. But the AI model on Collab, it predicted the root mean square deviation of the protein structure based on 9 structural and psychochemical features, such as surface area, molecular mass, and secondary structure penalties. It used a machine learning algorithm which input features F1 through F9 and RMSD to evaluate the most influential values through feature importance analysis. And then this was the Streamlit application that I mentioned earlier. So again, it uses the 9 protein structure features that cover surface area, exposure, molecular mass, deviations, distances, penalties, and spatial constraints. It also visualized data through histograms and correlation heat maps, and then evaluated multiple regression models like linear regression, random forest, grade boosting, light GBM, XGBoost, and displays their performance metrics along with feature importance rankings. And then to conclude the presentation, structural misfolding can be predicted using RMSD and derived features. These predictions may help identify disease-linked proteins earlier, and for future iterations, we could add real disease labels or test on real-world biomedical datasets.
Okay. So this was a really nice presentation. I really like the design that you have prepared, and also the way that you